Okay, so we have looked at structured knowledge in various forms. We have seen frames and we have seen description logic, in which we talk about categories of things, and we have talked about inheritance essentially. So, in the next few lectures I want to focus only on inheritance, and we will do a kind of a analysis of inheritance networks and see, especially in the real world when there are multiple possibilities, what can you believe about an individual, for example. So, the topic is called inheritance networks. So, let me start by asking you a question as to why do we need inheritance? Why do we try to implement knowledge systems in which we use inheritance? Otherwise, you would have to write rules for every category or every class and things like that. So, essentially it is for reasons of compactness essentially. Uh, we want to be able to say something, and then a whole set of subclasses should be able to inherit that property essentially. So, in the treatment that we are doing today, we will view networks as graphs, vertices and edges, and we are talking about inheritance hierarchies. So, our networks are actually hierarchies. Now, we will use a simplified notation here, where we will basically give a name to a node, which could be either an individual, or it could be a class, or it could be a property essentially. So, the vertices can be individuals, or class, or property. So, if you want to say something like birds fly. So, maybe you should spend a moment trying to think about what kind of a statement is this, and why do we want to store such a statement in a knowledge base essentially. So, when you say birds fly, what are we really saying?
Is a class called as birds which fly.
Elements of who fly essentially. But if you look at it from the logical point of view, in logic we would have written a universal kind of a statement, which would say that for all x, if x is a bird, then fly is x essentially. So, in logic the problem with this statement is that if this statement is to be true, if you look at the semantics of first order logic, every bird should be able to fly essentially. Now, when we say birds, what do we mean by this? It is a category of things essentially, or category of creatures or something like that. But if you dwell a little bit more into this, you will see that birds can be parrots, it can be an eagle, it can be a penguin, and so on essentially. Now, these are also classes or categories. So, if you were to be really a stickler for precision, you could see that the class of birds has elements which are themselves classes essentially. Now, most languages are not able to handle this sort of a statement. So, we sort of get around it a little bit essentially. Now, if you look at the let us say this is a universe of this course, then we have one class which is let us say parrots, another class which is eagle, a third class which is penguin. Then this birds is a class which is basically a union of all these classes essentially in some sense. We can think of it as a union essentially, or we can think of birds as a concept or a class whose elements themselves are concepts. Now, most languages, most description logics for example, do not allow this sort of a thing. Only if you go to owl full, you can sort of treat concepts as individuals. So, from one perspective it is a concept like parrot for example, from another perspective it is an individual. Most languages do not allow this. Anyway, this is just something that I wanted to point out that you must be aware of essentially. So, if you want to express statements in this graphical notation that we are looking at, we will express birds fly as follows. We will say flies. So, we said I said that the vertices can be individuals or class or property essentially. So, flies is a node in my network and bird is another node and there is an edge going from bird to flies. So, the statement bird flies we will remember, we will or birds fly we will represent like this essentially. Then a statement which says that penguin is a bird, also we will represent like this, and a statement like Peppy is a penguin, also we will represent. So, our graph will contain all kinds of statements. So, Peppy is an individual, penguin is a class, bird is also a class. So, we are saying penguin is a type of a bird essentially or subclass relationship, and flies is a property essentially. Instead of flies we could have written as creatures which fly or something like that, but that is unnecessarily verbose. So, we will just use the term flies essentially, and essentially we are talking of a hierarchy here. Which is represented using a graphical notation or inheritance hierarchy like this essentially, and we want to be able to ask questions about individuals. What can we believe about, let us talk about individuals, about an individual. Though it does not really apply to individual, it could apply to a class as well, it does not matter essentially. So, let us have this network that we just wrote. We said that birds fly or bird flies, penguin is a bird and Peppy is a penguin. Let us say we have another statement. Okay, so this is something that we will statements like this, which are general statements, and not universal statements. This is not a kind of a statement which says that all men are mortal. We are not saying all here. We are simply saying birds fly. So, there is a subtle distinction between that, and logically essentially we are trying to talk of a different kind of a statement which is true in general, which is not universally true, which means it can have exceptions essentially. So, we want to say leaves are green, birds fly, and students are hardworking, and this sort of a stuff, which may not be universally true, but which will have, which could have exceptions. We will come to this. How can we devise languages which will allow us to make such, and how do we make inferences in such statements? So, essentially if we say that birds can fly and penguins are birds and Pepe is a penguin, how can we make an inference which says that Pepe can fly? Of course, if you have only this much knowledge, then you can see that there is no problem in this with this knowledge base, and here the inheritance is strict. The word we use is strict, which means that if you are a subclass or something somewhere, if you are a node which is connected to a node above you, then you have to inherit the property essentially. So, if you are a bird, you have to inherit the property of flies. If you are a penguin, you have to inherit the property of flies from the node above you, and so on and so forth. And we have seen that the kind of taxonomies that we construct using description logic are allow you to do strict inheritance essentially. But what if we had a statement which says penguins cannot fly? Which is also a true statement. Now, you see we are talking about in some sense true statements. Birds can fly, nobody will dispute that. Penguins are birds, nobody will dispute that, and penguins cannot fly, also nobody will dispute that essentially. So, we want to be able to handle a knowledge base which contains these in some sense contradictory statements, and in the light of such statements we want to be able to talk about what can we believe about this thing. So, in the today's class and in the next few classes we will try to analyze this, that if we have a graphical form of inheritance hierarchies, what can we believe about an individual. So, this statement penguins cannot fly, we will write like this with a dash across the arrow which stands for not essentially. So, this is kind of a negation. Now, you see once you do that, inheritance is no longer strict, and we use the word defeasible. It can be defeated essentially. You can make an inference, but somebody may counter that inference, and you cannot argue that that person is wrong or you are correct essentially, or something like that. So, as you can see in this network, if you want to ask about what do you know about Pepe, then you can say Pepe is a penguin, there is no dispute about that. You can also say Pepe is a bird, you can see there is no dispute about that. But whether Pepe can fly or not fly, or whether penguins can fly or not fly, there is a dispute about that, because there are two paths going up from penguin. One goes via birds, which says that birds, penguin is a bird and birds can fly. The other path goes directly to flies and says you cannot fly. So, remember that this notation is negation here essentially. How do you, what do you believe in this essentially? So, of course, we are not asking this particular question about Pepi. We are asking that if you are given a network like this, what can we believe about a given individual? And we are looking for some algorithm which will help us decide as to, as you can see, there are two paths going from Pepi to flies, and we want to be able to decide which path is better essentially in some sense. One path is Pepi, penguin, birds, flies, and the other path is Pepi, penguin. Any suggestions? So, the most one heuristic which suggests itself says that shorter paths are better essentially. So, we can try the shortest path heuristic. It says the shorter paths are better. So, let us stick with the same knowledge base. Flies, bird, penguin, Pepi, and not flies. Okay. So, here the shortest path is Pepi, penguin, bird, flies. So, we will say that choose this path essentially. But what do you do if I give you an alternative? If I added another statement to the knowledge base, or I modified the knowledge base which said the following: flies, aquatic.
Sir, in the first example, is Pepi, penguin, not flies is not the shortest path.
Pepi, penguin, not flies. That is the shortest path. Yeah, sorry. Correct. So, the shortest path says that Pepi cannot fly, and that is something that we are willing to accept in the real world that we have. We believe that Pepi, being a penguin, cannot fly. Supposing my knowledge base was this, I distinguish between, let us say, birds and aquatic birds, and then I say I could have a knowledge base like this essentially. So, I have added something more information. I have said that okay, penguins are aquatic birds and aquatic birds cannot fly essentially. Now, you see that the shortest path heuristic fails. Okay, let's not say it fails, because if you were given this particular network, then there are two paths which are of equal length, and there is no particular reason to believe that one of them is true and the other one is not true essentially. We are only looking at the topology of the graph essentially. We are not looking at real world knowledge in which we know that penguins cannot fly, but that is not the point here essentially. If we had a network like this, then shortest path network would missing. So, anyway, so this network is ambiguous. But if we still take another network, so I have modified this to this, and let us say we modify this to yet another network in which I say flies, aquatic birds. So, they do not fly. Then we have Antarctica aquatic birds, which are aquatic birds, and then of course, we have birds, and then we have penguins. So, when I write bird, I basically mean birds which excludes the notion of aquatic birds, otherwise you would have had an arrow from there to there also. So, let us say non aquatic birds or something like that, but I am not writing it here. What have I done from the first network on the left, which is in blue, to the third network on the right, which is in black? The only thing I have done is I have added more knowledge essentially. Okay. I have sort of added some more categorization in the taxonomy, and I have tried to distinguish between aquatic birds which are in Antarctica and so on. I have not added anything which is negating anything else essentially. And yet you can see that shortest path is changes. The new conclusion that you draw in this new knowledge base is that penguin is a bird and birds fly. So, that is a shorter path. So, Pepe flies essentially. Now, this is something which makes the shortest path heuristic very fragile, because it depends on the granularity at which you are representing knowledge essentially. If along certain parts of the taxonomy you have very fine grained distinctions between categories, and let us say butterflies and red colored butterflies and red colored large butterflies and so on. If you have many categories, then they will make longer and longer paths essentially. And whereas on the other hand, if they are shorter paths where you do not have enough knowledge, they will have shorter paths, and then the shortest path heuristic does not quite work essentially. Let us look at another problem with shortest path heuristic. So, the first, as we observed, was that it depends on how much knowledge you have put into the system, and even though the knowledge may not change in its consistency, both knowledge base may be consistent, depending on the level of detail along certain paths, they may get excluded from the shortest paths essentially. Okay, so, let us talk of elephants a little bit. In general, we would like to say that elephants are grey and royal elephants are elephants, and this is an example from Brackman and Levesque. Fat royal elephants are royal elephants, and Clyde is a fat royal elephant essentially. So, that is the first part of the knowledge base. The other part is that royal elephants are not grey. So, instead of saying that they are white, we will use this either a property or its negation, because basically we want to decide whether they are grey or not. We might have a separate part of the network in which we would say that, for example, royal elephants are white, but that is a different story altogether essentially. So, essentially we want to decide whether they are grey or not essentially. So, whether Clyde is grey or whether Clyde is white. In this case, as you can see, the path going to white is perfectly believable, because there is in fact no contradiction here, but the path going to grey has this ambiguity about it, which is that there are two paths. One path which goes via elephants says that elephants are grey, and the other path which goes via royal elephants says that royal elephants are not grey. And the shortest path heuristic actually would work here, because the shorter path which goes via royal elephants would say that yes, they are not grey. But now, nobody has said that what is the nature of my knowledge base essentially, what kind of statements can you have. You can see that looking at this knowledge base, which says that royal elephants are elephants and fat royal elephants are royal elephants and Clyde is a fat royal elephant, I can make an inference that Clyde is an elephant essentially, because of this property. And what if I add this network here? Clyde is an elephant. There is nothing wrong in adding this detail here, but now this reverses again the shortest path conclusion. In some sense it is similar to what was happening in the last time, because we have a shorter path, which means that is less detailed. We are saying Clyde is an elephant and elephants are grey. So, that is the shortest path you can find. So, it must be grey essentially. So, essentially what we need is something which is more robust compared to a shortest path this thing, and we are basically building up a case for a more formal analysis of inheritance networks, which will be more robust essentially, which will not be brittle when you add more statements, then the system changes its inference and that kind of a thing. So, people have tried other kinds of heuristics. So, for example, we know that we are interested in specificity. One way of looking at specificity is, so that is what we did in when we were talking about frames. We said that if you have a frame which is an instance of another frame, or which is of another frame, then whatever you write in that property will override whatever comes, whatever is inherited essentially. So, in that sense you can say that royal elephants are kind of elephants. So, if you say something different about royal elephants, then you must accept that essentially. Another way of expressing the same thing is by inference length, which says essentially in this example that you have two possibilities, grey royal elephants and elephants, which are competing essentially. Royal elephants are not grey, elephants are grey, and we are talking about Clyde. All the reasoning that we will do will be with respect to individuals here. We want to say that as far as Clyde is concerned, this property is true. So, as far as Clyde is concerned, elephants are not grey essentially, or we cannot say that elephants are grey, which is not the same thing. So, the inference length says that if there are these two competing hypotheses, and if there is a path which goes from one to another, and we can see that there is a path here, that you can reach elephants via royal elephants, then so path goes via royal elephant, therefore, believe what R is in some sense says. So, between grey and not grey, there is a path which goes from royal elephant to elephant for Clyde, again with respect to Clyde. So, you must believe what royal elephants say about Clyde rather than what elephants. This is again just another way of saying that the royal elephant is more specific than elephant essentially. So, whatever you have said with royal elephant, you must accept that. What is what has happened with this arrow that we drew from Clyde to elephant? It has added some knowledge which was not really needed essentially. So, for example, if we were looking at the algorithm for constructing a taxonomy in description logic, then we said that we will only create those edges which are immediate essentially. We will not create transitive edges. So, in some sense this is a transitive edge, and we can see that at least with the shortest path heuristic, it messes up the computation. Okay. So, in the next class we will look at a more formal way of looking at these networks and give a more formal definition of which paths are acceptable or as we will say admissible essentially. So, we will do that in the next class essentially.